perhaps a name of one of these 10 diagrams? Phil, what do you think?
The number 9 is the external part of a secant segment.
You are correct. Number 9 is the external part of secant segment. Awesome. Who else has figured out some of these? Joel.
5 is externally tangent circles.
Nice. Externally tangent circle. Nikki.
Number 7 is point of tangency.
Correct. Point of tangency. Ruby.
Number 2 is the secant line.
Nice. Secant line. And the way you can remember this is that, hold on, I messed up on my handwriting. But the way you can remember that is that a secant slices and a tangent just touches. Okay? Emma?
Number 1 is internally.
Nice. Internally tangent circles. All right. Victoria?
Number 4 is a tangent line.
Perfect. Ruby?
Number 3 is common internal tangent.
Nice. Common internal tangent. Yes, Autumn?
Number 8 is common external tangent.
Perfect. Common external tangent. Anybody else? Let's see. Katie?
Number, do we already do
Number 10? I don't think so.
tangent segment?
Tangent segment. And Ruby?
Number 6 is secant segment.
Yeah, it's the secant segment. The whole thing is the secant segment. And did we finish it? We did. Hey, nice job. You didn't need me to teach you that. Now, something that you need to note the difference is that when a secant line, a line goes on forever and ever in either direction. Secant segment has an endpoint and a beginning. Same thing for a tangent line. A line goes on forever and ever. A tangent segment has an end and a beginning. And it's important that you understand the differences between these vocabulary words so that when you're given a problem in a book that just describes it and doesn't give you a diagram, that you can be able to generate your own diagram from the descriptions. All right, any questions so far? All right, then turn the page. And we have just a couple theorems to talk about today. First off, a tangent line is perpendicular to a radius drawn to the point of tangency. When we looked at the Java applets before beginning Chapter 10, one of them showed you this, that the radius drawn to the point of tangency, no matter how you change the circle, is always perpendicular to that tangent line. Now, whenever I involve a right angle, what does that give me the opportunity to use? Yes. Pythag, or right triangles, or 30, 60, 90, depending on what's given in the problem, right? Pythagorean triples. So keep that in mind. And then the reverse, if a line is perpendicular to a radius at its outer endpoint, then it is tangent to the circle. All right. Now let's do the proof here. And we're given in circle O that PX and PY are tangent segments. What do you know about OX and OY? Nikki.
They are tangent to the circle.
OX and OY?
Yeah.
That they're congruent, yes. OX is congruent to OY. And Nikki, why are they congruent?
Because all the radii of the circle.
Perfect. Radii of same circle congruent. Great. Let's see. So we have those equal to that. What about OP? Yes. Joel?
It's OP congruent to itself.
All right. That will be reflexive. Now we haven't used today's theorem, which is that PX and PY are tangent segments. If we know that they're tangent segments, what can we imply from that? Yes, Katie?
Can we imply that PX and PX is perpendicular to OX?
Perfect. So PX is perpendicular to OX, and along the same line of reasoning, we could conclude that PY is perpendicular to OY. And your reason would be, if a line, if our tangent line is perpendicular to a radius drawn to the point of tangency. So tangent line perpendicular to radius. That's good enough. Okay, now if both of these are right angles, and we just said that OP is congruent to itself, have we proven the triangles equal to each other?
Yeah.
All right, who knows why? Phil?
SAS.
Well, I don't see SAS because we have to have PY and PX for SAS. See, Hannah? Yeah, we would have hypotenuse leg. We have one actually step to say because we haven't said right angles, and HL requires a right angle. So we have said perpendicular. So let's throw in that angle Y and angle X are right angles. Perpendicular implies right angle. And then just like Hannah said, let's go ahead and say that the triangles are congruent. PXO is congruent to triangle PYO by HL. And for HL, the first thing you put is the right angle. In which step did we prove the hypotenuse? Step 3. And the leg we said in step 2. Now we are trying to prove that PX and PY are congruent, which we have. Why? CPC-TC. Nice. See, we're not doing any different proofs than we did in the first semester. Well, we just proved a theorem, and we call this the Two Tangent Theorem. And that is, if two tangent segments, oops, cancel that comma, are drawn to a circle from an external point, drawn to a circle from an external point, then those segments are congruent. Meaning if the tangent segments begin at the same point and are tangent to the same circle, then you know that they are congruent. And you no longer need to do this type of proof to conclude that. Nikki?
So can we just say two tangent theorem when we're doing it, or do we have to write out?
You can write two tangent theorem. That's fine. If you don't remember a two tangent theorem, then say, well, you could say if two tangents drawn from one point to the same circle are congruent. All right, so now let's look at the practice problems, where we're going to apply the fact that a tangent line is perpendicular to a radius drawn to the point of tangency, and that two tangents drawn from a common external point are congruent. All right. Number 1, CA and CB are tangent to circle P, and notice that they're drawn from one point. From what we just learned with the two tangent theorem, what's something that you can conclude? Victoria?
CA and CB are congruent.
Perfect. CA and CB are congruent. Autumn?
And then because if sides then angles, you can use the angle CBA is congruent to BAC, so you can say the other side is 60.
Okay, yes, we could say that this angle over here is also 60. Good. Now we need to generate, we're trying to solve for x, the radius, right? And we need to generate a little more, oh, okay, Max, go ahead.
Can't we use the, since that wouldn't, since AX and TB are both radii, then can't we conclude that that's a 30, 60, 90 triangle?
Since, oh, so that's, this triangle must be a 30, 60? Because this whole thing would be perpendicular. So we're left over with 30 degrees here. So that means that 6 is what side of the 30, 60, 90?
It's the long side.
The long
So
side.
the short side would be 3, wouldn't it?
Well, it would be 6 divided by the root of 3.
No, but yeah.
Yeah. Right? So let's figure this out. 6 divided by the root of 3 would be what? We have 6 root 3 over 3, which would be 2 root 3. Now, x is the hypotenuse, right? What do you do to the short side to get the hypotenuse? You double it. So x is just 4 root 3. Nice. Isn't it great that we know chapter 9? Okay, number 2. AB, BD, and DE are tangent to circle P. So guys, let's first look at tangent segments BA and BC. They both start from point B, so what can you conclude? They're congruent. So what's the length of BC? 3. Now ED and CD both start at D and are tangent to the same circle, so what can you conclude about the length of CD? That it's also 4. Alright? Now, what's the length of BD then?
7.
Yeah, all you have to do is say that x is equal to 3 plus 4, so x is 7. From here to here is 3, from here to here is 4. Add them up, you get 7. Any questions on that one? Zena?
Sorry, how did we get 4 again?
How do we get 4? Because ED and CD are both tangent, and they both start from point D. Okay, number 3, I'd like you to label this a walk around. So in this walk around problem, we know that this circle is, or a triangle is circumscribed about circle O. Now, when a figure is circumscribed about a circle, the segments that make up that figure are tangent to the circle. So we know that all these lines that touch the circle are tangent lines. So what do you know, for example, about the length of ZA compared to ZC? Congruent. They both start at point Z. What about AX and XB? Congruent. What do we know about CY and BY? Congruent. So let's label what else we have. We have that the whole length of XY is 7. The whole length of XZ is 5. And the whole length of, whoa, that one didn't turn out so well, is 8. And we want the smaller parts. So this is what you do. Pick a place to start. And I am randomly saying I'm choosing XB. And I'm going to call that my variable. I'm calling that X. Well, if I know that XB is X, what is AX? It's also X, because we already know those segments to be congruent. Now you could start anywhere in your walk around problem. I chose to start there randomly. Now, if XY, if the segment XY is altogether 7, then how could you use the variable X to represent the length of BY? Autumn?
7 minus X.
7 minus X. Nice. Well, isn't BY and CY equal? So what would CY be? 7 minus X. All right. Well, what does ZC and CY add up to? It adds up to what? 8. So ZC is going to be 8 minus 7 minus X. This part is going to be 8 minus, put it in parentheses, 7 minus X. And it looks funky, but we're almost done. Now then, what's the length of ZA? Nikki?
8 minus 7 minus X.
8 minus 7 minus X. So try to fit it in. 8 minus 7 minus x. Well, we haven't used the last fact, and that's that ZA and AX add up to 5. So take the variable representation. So we know that ZA is 8 minus 7 minus x, and that AX is just x, right? Those are going to add up to 5. Write that equation out and solve it, and you will begin to have the segments of your walk-around problem.
You also add everything up and put it next to 20?
You could. I believe so. That will work. So now distribute the negative. So we get 8 minus 7, which is 1. And minus of minus becomes plus x. So now add up like terms. Subtract 1 and divide by 2. Now use that value of x, 2, and plug it in everywhere else to find the remaining values. So if x is 2, I know that AX is 2. We have found one length. And then what is going to be BY? 7 minus 2, or 5. So these are all 5s. And then it wants CZ. Well, CZ and CY have to add up to 8. So what's CZ? 3. Any questions on the walk around? All right, we're going to skip number 4 just for a moment, but I'd like you to go ahead and try number 5. It says TP is tangent to circle O, whose radius is 8. Let's draw a radius to the point of tangency. That helps us because we know that a radius drawn to a point of tangency is perpendicular. So we could draw in that radius and mark our right angle. We also know that the radius is 8, so fill that in. And TP is 6. And we also know that OX is how long?
8.
OX is also 8 because OX is a radius. What we don't know, you guys, is this little part outside the circle, XP. So that's what we'll call our X. Max?
Triangle thing?
Yeah, we could use a triangle thing. What is that?
3, 4, 5.
Well, no, we actually, we don't know.
But we got a 3 and a 4 there. We got that 6 and 8. So the last one.
So you think this whole thing is 10?
2.
So what's X? 2. It is, but what happens if it wasn't a triple? Can you help me set it up if we know it wasn't a triple? Just indulge me in case you can do all the other problems. Go ahead, Katie.
So we can do Python.
Yeah.
So 6 squared plus 8 squared equals x squared.
Well, this whole hypotenuse would be,
X squared minus 8.
well, the whole hypotenuse would be 8 plus x, right?
Yeah.
And then you have to square that. So if you didn't recognize that it was a triple, or if it wasn't a triple, then you would have had to do some fancy algebra here. Okay? But Max, good catch on that. All right. Go ahead and try number 4 on your own.